So just right click and then update, and we can see the sloshing here. Okay, it will take some time because I'm actually running another simulation.
So is it necessary to mesh it very fine?
No, I have the coarse one. What's this one? Yeah, this is very small. And let me show you the file. This is the file, the input file. Yes, the mesh is very small. Okay. Wait, so this is the input file. We can see this is the size of the mesh. And with ICFD, actually, we don't mesh the solid, we just mesh the surface.
I see.
So we have this is the bottom, this is the top, and this is number 3 is the interface.
Oh.
Yeah. So here I'm doing like this. We have 3 parts because the boundary condition is different. Here it will create water, and on the top it will create the air or the vacuum, not the air. And then here it's the interface between both of them. So you can see the mesh is very straightforward, just 1, 2, 3. And the keyword as well is very, you can see this, all the keywords.
Oh. Too few.
But most of them is under ICFD. But still, yeah, it's
I remember a little.
Yeah, it's still not that much compared to the normal structure analysis. Yeah. So let me hide these guys. Wait, F2, hide everything. And then I want to create the same tank, but very simplified one. So I have here solid sphere, and then accept. Okay. Oh, no, this one is not good. Yeah, I need to have 6. I need the number here to be even because I want to split half. Yeah. This is the one I want. Remember when I mesh just now, the density, I put 6, right? So this 6 meaning how many elements we have in the square of the form square shape. You can see here 1, 2, 3, 4, 5, 6. So that's the meaning of this 6. Okay, now I go to element generation, shell, solid face, and then let's say I create like this. So now I have number 3, which is shell. I want this one. This one is like a dummy. I can delete it. So what I want to do, I press on F8, front view. Then I hide this one. And then I make another shell. So now I have this one and this one. Okay, so last is copy, move. Let's say I put a new part ID here, and then I change the ID of the lower part. Then I will have like the same as in the original file. We have shell on the top, shell on the bottom, and between them we have the connection. So this is a structural mesh, which is the normal FEM mesh that we use. In order to use ICFD, we need to use this one multi-solver mesh. So it will change our mesh from structural to multi-solver mesh. The multi-solver mesh can be used for ICFD or electromagnetic or anything. So these steps actually can be used. I mean, sorry, where is it? This tool must be used if we want to use this multi-solver or multi-physics simulation like the ICFD or the chemistry or all those new things. So here I click by part, and then I select part number 3 and part number 4. Apply, sorry, I need to click enter here, then apply, and then accept. Now if we click on F2, I have this MS mesh, and I have number 5 and number 6. These two guys are new things. 1 and 2 and 3 are the original one. Okay, so when these two, the one I just created, 5 and 6, and we can see now it appears here, ICFD part, we have 5 and 6. And then we just put all the ICFD keywords. So this is for the heat, this for the heat, this is also for the heat. This is a free slip boundary condition, meaning if we model like a rectangle, or if we model a big square in a 2D and you want the up and down side to be like doesn't have any friction, so we use this free slip. And we have the non-slip boundary condition. Where is it? Yeah, non-slip. This is if we have like a tube or the wall of our tank. And we need this FSI. This FSI needed when we have a structure. But in this case, in this simulation, it's actually purely ICFD. So we don't need this FSI. Because in this simulation, I'm moving the whole mesh using this control imposed move. Okay. So I think it's better that we start something new, right?
Oh, yeah, I think it is too difficult, brother.
Yeah, so we start with 2D first.
No, 3D is better because 2D I'm not interested.
Okay.
3D, but very simple and maybe with few elements that can be done immediately.
Okay. So.
But I mean, seems ICFD is still very difficult for me. So.
Okay, let's try, see. Let's try here. Okay, so you want sloshing or flow problem? Sloshing like the one I showed you. Flow?
Okay, flow is better, I think.
Okay. So we...
Because sloshing, ALE I can do very nice.
Okay. So we want 3D, right?
Yeah.
Okay. So we try to make a flow over, what you call it, sphere. So first I want to make this shell, sphere shell. And this will, I mean, the flow will go around this guy.
Oh, yeah.
Except now I want to make a box.
Yeah.
Say this is too big and it's not in the center. Let me try to do in X and Z. I need to center it. 50. No, not in, yeah. Oh, it's okay. We just do like this first. I just want to make it center. Okay, good. Now I want the flow to be in the X direction. So this side should be a bit longer. So let's say it's 100 minus 100, 100. Okay. Now instead of the number, I control the size. This is maybe can be 20, I think. Yeah, this one should be fine. Or I think this is too much. I mean, too big. Okay. And the one thing is, because if the mesh difference is very big, then it might be a bit problem, because the LS9 will create a solid mesh filling this volume. So the problem is, if the mesh is the box is very coarse and the sphere is very fine, then the transition between the elements will be very big.
Oh, yeah, there should be something similar.
Yeah. So in this case, because we want to make it simple, I just make everything static. We delete these two guys. So I have this one and this one. Okay, if I click on F2, all right, this is okay because it's a shell. This one is a box. I don't want that. If this is a solid, I want it to be, what we call it? I want it to be shell elements. Okay, actually, I can directly create the shell boundaries for the ICFD, but I prefer making the solid first, because like this, I can visualize the mesh size. And also it's much easier for creating like this instead of creating one by one using like this, using this one. If I use this one, then I need to know the coordinate of every point. Yeah. So I create the solid first, and then after creating the solid, we just create the shell based on this solid. So create element generation, shell, solid face, and then let's say this is the input, this is the output, and these are the boundaries.
These input and output, how you did it?
Oh, I just click here. Let me try to redo it.
So you are making them shell parts.
Yeah. So
okay,
if I
yes,
see this one, this is solid, so I don't have.
Yeah.
So part number 4 is like dummy part. We don't need it. So I just create it so I can create these guys much easier. Okay, so now I can just right click here and then delete. And then, yeah, you can delete from here easily. If you are using some old versions, then I don't think you will have this one. Anyway, so now
we are left only with the shell.
Yeah, so all these guys are shell, and this
and the sphere is also shell.
Yeah, sphere shell, because I created a shell. Okay.
Yeah.
Now the last step is this one, and then create hole. I mean, select hole. You can actually select one by one, but if you do like that, then I mean, you can just select, then apply, accept, then you do again, select, apply, accept. But if you do like that, the nodes will not be connected between the boundaries.
Yeah.
So you need to do all of them together, I mean, in one go. So if you do like that, then all the boundaries will be connected. And if you see here, I click on whole, and we have 4 parts.
Yeah.
Which is the inlet, the outlet, and the boundary, and as well the sphere. Yeah. So apply, then accept. And so now if you open model, we don't have any part or normal elements. We have this mesh. This one is actually the surface mesh for the ICFD mesh. Okay. So all what left now is just the keyword. So we have here part. This is number 8. We have 8, 9, 10, 11. So here we have 8, 9, 10, 11. So it's a good practice to rename them. So it does, this is sphere, this is inlet, this is outlet, and this is the boundary.
The body, yeah, the boundary.
Okay. All right, now click on all, and then we have the ICFD controls. But before that, I want to define the material. So new material, and then this one, fully compressible fluid. And this is the density, let's say is 1000. Viscosity of water, 0.00089. And then accept. These guys, you don't need it. This is surface tension. This is actually if it is a free surface problem. Free surface problem meaning we have like the sloshing. We have air and we have water and you have vacuum. That's a free surface. But now it's like a flow problem. We don't need any surface tension. Okay, this done with the mat. Now the section. Click on new and then accept. That's all. We don't have any section type because it's already under ICFD. So this section is ICFD because it might look redundant, but press on the wrong guy. It might look redundant, needing to define this while you don't have any options here. But when you know that this mesh actually can be used for other stuff as well, like if you use this one, CESE method, then you will have section as well. Somewhere here you have the section, and for that one also, I mean, you can define a section there. Let's say I go with EM, electromagnetic, because I've used that before. So here we have, I think we should have like some section here as well. So my point is we need to define this one because we want to tell the software that this multi-solver mesh is for ICFD and it's not for like other things like the electromagnetic or the other type of the multi-physics analysis. So now we define section and mat, so we just need to assign them. Luckily, everything is water in our case. What I mean here, the volume enclosed by these 4 parts all will be water. So we don't need to worry about the material properties. I mean the material type. Okay. And
so
then,
the sphere, how the sphere is going to be defined?
We have the sphere here. Yeah. The sphere, nothing inside the sphere. Actually, if we solve this and later on we'll see that the water will flow around this guy, and inside there will be vacuum, there will be nothing, because right now this is purely ICFD or pure CFD simulation. We will not have any fluid structure interaction. The flow of water will pass through this sphere because this is the boundary of the ICFD. It's not because we have like a steel ball or like a rubber ball.
Okay, this is the boundary.
Yeah, because if we want to do like that, then we need to create the sphere using the normal, using the normal standard FEM, and we need to put the, what do you call it, the material, the usual, the steel, and all that things. Yeah. And if we do like that, then we will see that the water will pass through this guy and also will push it backward.
Oh.
But in our case, this is we don't have any structure. This is a pure CFD simulation. Okay. So here the boundary condition. Each of the ICFD part must have boundary condition, otherwise it will not work. So we have free slip. Free slip is for the boundary. Insert and then accept, because we want the water to just flow here and do not have any friction. Okay. Because this we want actually it's like the non-reflective boundary condition, because we want actually to model a big tube, a big square tube, but to save the time, we just model this small one.
Yeah.
So the water will just flow here without any friction. Okay. This FSI, if this one will interact with a solid sphere inside it, then I need to define this one to be number 4, to be here, number 8. But in our case, we don't have any solid inside here, so this one is not needed.
I see.
Okay, this is wave. No, this non-slip. Yeah, this non-slip is our case. So number 8, insert, accept. So there will be no slip here between the water and the sphere. And in real life, it should be like that also. So this is here. Okay, this one, because no matter how much the surface is smooth, in real life, of course, we will have friction. I mean, the water at the water and the boundary close to the surface will have will have zero velocity. So that means by non-slip. Okay, prescribe pressure. Okay, so the input is here, the output is here. Let me click on F2. Yeah, number 9 is the inlet, number 10 is the outlet. We want it to be in the positive X. Okay, prescribe pressure. So the pressure, we define it on the outlet. In the inlet, we define the velocity. In the outlet, we define the pressure.
Yeah.
Because each part have to have a boundary condition. So we cannot apply velocity here because we already have velocity in the inside, in the inlet. Load curve, we need to define curve. So click here and then new keyword, then curve. Here we say constant curve. So here I put 1 and then insert very big time of 100, and it's also 1. So this curve is actually straight. Okay, this curve is straight.
What is this one?
Okay, wait. I put here 1. Why? Because here I can use SF. Okay, this one will multiply the curve. So if I put, like, say here 5, I know now the pressure is 5 because my curve here is just a straight one. You get the point? You get my trick?
Yeah.
But here the pressure, we want it to be 0, right? So we put 0. So it will just multiply the curve by 0. So we will have 0 pressure. Then replace.
Here in the first, on the inlet.
This is the outlet.
Outlet.
Yeah.
Outlet pressure 0. Okay. The inlet velocity something.
Yeah. So this is prescribed velocity. This is the inlet. So here we put the inlet, and then degree of freedom in X. DAD is linear velocity, and the curve is 1. And then this is the velocity, let's say is 2, can be any number. So we put 2 meters per second and then insert, accept. Okay, this is okay, but it's better to define two more of this velocity in the inlet, which is I click on add the same part number 9, and then degree of freedom y. Yes, the load is 1, and here I put 0. Insert accept. What I did here, actually, I forced, this is the inlet, I forced the velocity to be in this direction. I don't want any velocity like this or any velocity like this.
Oh, just straight.
Yeah, just straight. Because here we have like the ball, right? And because of the ball, the velocity inlet might go up, like be in an inclined direction. But I want to force it to be in X. So here I put 0, meaning the velocity in the Y direction is 0. And then I click add, the same thing, number 9. And then degree of freedom now 3. And then this is 1, the constant curve. This is 0. Insert, accept. Okay. Control adaptive. This is actually if you want to remesh. Adaptive size also if you want to remesh. So I just put 1. Remesh if elements are distorted. Okay, conjugate, this is for the heat transfer. We don't want it, we don't need it. Control FSI, this one also no need because we don't have any structure. This is actually to control one-way or two-way FSI. We can actually make it one-way, meaning the force from the fluid will go to the solid, but the forces from the solid will not go back to the fluid. That's what it means by one way, and I really don't know what's the application of one-way coupling. Anyway, so control general, this is transient analysis, so it's the default is okay. And then imposed move, this one no need. This one, as I told you before, is to move the whole mesh, like in the sloshing. So if we are doing the sloshing, then we need this one. Control mesh. Okay, this is
control general. I think it was not recorded, this command.
Yeah.
You have to accept it.
Yeah, but actually because we are using the default, then actually no need. It's like control time step. If you define it or do not define it, if you do not change the default, then it should be fine. Okay, control output. This is actually the what we call it, the information in the command screen. So actually no need. But if you want more information, we can just put here equal to 1 or 2, like full output with details and everything. Okay, control time. Let's say the end time is 20 seconds. Oh, okay. I might have a problem here, but it's okay. Yeah, it's okay. No need. And DT, let's say 0.
0?
DT 0 meaning it's automatic.
Oh, I see.
Yeah. If DT 0, then time step is automatically computed. If I want a fixed time step, then I can put any value here. Okay. Yeah, this is turbulence model if you want to use a different type of turbulence. And this is important to get good results. It depends on like your simulation, like your velocity and the Reynolds number. Okay, here is the output. Okay, we have drag, and we put here sphere number 8, and DT output, let's say every 0.1 insert. This one will find the drag force around the sphere, which is like the interaction forces. Okay, and this flux is for the heat. This is if you want to input the time step information, we can also use this one. I mean the time step will be written in the some file, in output file. Okay, initial no. This one, I think, let me have a look. I think that's all from here, if I'm not mistaken. Now we go to all, and we have this mesh here. Okay, we need to create, oh yeah, here in the ICFD, I need to make here part volume. Without this part volume, it will not work very well. I mean, it will not work at all. So put new. In this, I call it volume. ICFD volume. And this one is 1, and this one is 1. Okay. And here I put all the part IDs. So 8, 9, 10, 11. Then insert and then accept. What's the meaning of this? Meaning the enclosed volume by these 4 parts, 8, 9, 10, 11, will have material ID number 1, which is water. If in case we have like we have water and air, vacuum, then we need to have 2 of these ICFD parts. Okay, we just proceed first. I want to show you the sloshing file, but let's keep that for later. And then here is for creating the mesh. Okay, if you remember when we create a solid mesh, let's say create anything. If I create this one, this is, I'm just showing you, for example. I will delete this one later. I create this sphere now. We have this solid sphere. Okay, the one I just created. Okay, this one is the normal FEM that we use. When we use the meshes now, we create this one. You see that this these elements were created, right? And also this part. But these actually are not really linked to each other. Meaning, if I want to delete this one, then this definition will still be here.
Oh.
So let's say I right click and delete this one. You see now, we don't have the sphere anymore.
Oh.
The dummy sphere. We have the nodes because the nodes are still there. So here are the nodes. So if I delete these nodes, these guys will disappear. Okay, let me hide. You see, number 1. I think I delete that. Okay, this is our sphere number 8. This is the dummy. I think is mixed up. Oh, damn. I deleted the wrong guy. I want to delete this one. Anyway, but the thing is, even if we delete the elements, this part is still here, right? So my point here, the point that I want to explain is, oh man, it's got stuck. Let me try again. Am I recording or you are recording? I'm recording, right? Yeah. Yeah, I think I'm recording. Yeah, I'm recording. Okay, so we do it again very quickly. Mesh, shape measure, and here is minus 100, 100, minus 50, 50, minus 50, 50, and this one 10, 10, 10. Okay, done. And then solid sphere, solid shell, and create. We have like this. Okay, accept. All right. Now I want to do a extra step that I did not do before, which is to scale this guy. This is not necessary, but because I want everything to be in meters, kilogram, in seconds, I scale 0, 0, 0, and then 1000. Click on whole, and then scale down. Oh, sorry, scale down in all direction. I can see it become small. Now, if I measure this one, it will be 0.2. So it's 0.2 meters. Okay, now we are done with the mesh. So no, not yet. This guy, the box is solid, right? So I go to element generation, shell, and then solid surface. So we have input here, we have output here, and then we have the borders, and I hide the box here, hide everything, show the sphere. So this one will be the sphere boundary. Okay, so this solid box is like a dummy. I can just delete it. Delete. Yeah. Oh, sorry. This one no need. This one, the last one, no need because the sphere is already shell. So actually, I can just right click here and delete. Okay, yeah, that's correct. So I just want it to start from 1. So part number 5, I make it number 1. So this number 1 is boundary. This one is inlet. Green is part ID number 3 by default, and 4 is yellow. By default, part ID number 4 is yellow color. So this one output. So now I go to mesh, multi-solver. So convert the mesh to multi-solver. Click on whole. We have 4 parts, 4 shells. So that's correct. Apply and then accept. So now click on F2. You'll see we have MS multi-solver mesh. So this 5 is a bound, 6 is the sphere, 7 inlet, this is outlet. Okay, good. So now let's go to the keyword very quickly. Model, or not model, check. This one, click on all, and then ICFD. So FSI, no need. Free slip in the boundary, insert, accept, and then non-slip is around the sphere, insert, accept, prescribe pressure in the outlet. We define a new keyword, curve, new constant. So this is 1, insert, time equal to 100, insert, accept, and then we click on insert here as well. We want the boundary to be, the pressure at the boundary to be 0. So the scaling factor should be 0. So we replace and then accept. Now for the inlet velocity, part ID number 7, degree of freedom 1. This is a linear velocity, the constant curve, and then let's say the inlet velocity is 5 meters per second. Then insert, accept. Now we want in y direction to be 0. So scale factor is 0, insert, and then for z as well to be 0, and then accept. So we have defined inlet velocity to be 5 in the velocity perpendicular to, in y and z to be 0. Okay, control this one, no need. I think I will just use this control mesh. Okay. And then control output, control time, the termination time is 20 with automatic time step. Turbulence, let's say, is number 4. Drag, we want the drag forces around the sphere. We want to know the forces around the sphere. Insert, correct, right? Yeah. And then database time step, just want the output. Database, or this is no need. Okay, initial also no need. Material, water, new, fully compressible, 1000, 8, 9, accept. And then section, insert, accept. Okay, we define the section to the section and the material to the surfaces. And then we define the volume. New volume is ICFD volume. So section number 1, ICFD section, and this will be water. So this enclosed volume will be water. 6, 7, 8. Insert water, accept. Okay, so this one, I think that's all. Now we were here. Okay, now we want to create the volume. So here, volume new, and then here 5, 6, 7, 8. Insert, accept. Volume partner lead. Okay, so we stopped here last time. So I tried to explain about the connection between elements and part. If you remember that if we deleted the elements, the part, this where is that? This part will still be there, right? That's where we stopped. So here in ICFD is the same. Mesh here is like the elements, and part ID here, sorry, not this one. Part volume here is only the definition of the part. Okay, so that's why we still need to make this one and also to make this one using the keyword. Okay. Boundary layers. This is important to get good results around the, if we have the flow around the cylinder or around the sphere. Okay, number of elements, let's say 1 is enough, and then insert and then accept. Okay, where is this? This is the sphere, right? and the water flow around the sphere. And when I put here number 1 for sphere, this is the sphere, and I put number 1, meaning the elements in the boundary will be split one time. So we will have finer elements here, close to the body or close to the boundary here. Okay, so click on model. I think this is all. Now we define the general control, which is the termination time. Wait, sorry, termination. We don't need the termination time here because we already have the ICFD control time. Okay, so we don't need this termination time here, the standard control termination. This one we don't need it. Okay, but if we have a solid sphere inside here, and we have FSI, fluid structure interaction, then we need to have the termination time of the structural analysis, and it should be same like the value we put in the ICFD. What I want here is only the database. So database D3 plot, and let's say put 0.1, and then accept. I'm not sure if it is small enough. Then save. Open this one, and then paste here. CFD flow. Save. Model check. Okay, we don't have any warning and any warning or any errors, so hopefully it's fine. Click on the model, define curve, ICFD. I think that should be all if I did not forget anything. So I open this one, browse, paste. Okay. One more thing important, when we use ICFD, always need to use double precision. Single precision doesn't support the ICFD.
11 has some problem, they say. Release 11.
Oh, okay. Sadly, this is the only one that I have. So you can see some information here. You see here it says a time step because I asked for it to show the time step. And here it says, like, you see the first line is like the material ID and then the boundary conditions. Okay, so now if we open this one, oh, we have 15 states already. Maybe the time step is very small. Okay, so now the shell, this one, we need to hide it to see what's inside. Okay, we start one by one. So here we can control what we want to see. And actually, I mean, we don't have the fringe, like the stress or velocity from here. Like we don't have here for the multi-solver. You can see we don't have. So to show the colors and like the velocity and the pressure, we use from here. So you can see here, what we call it. This is, I click on boundary and I show the fluid velocity. And I can show like other things like the fluid pressure. Okay. And yeah, whatever I want to show. And here also, if I hide the boundary, I can show the, let's say, the pressure here, sorry. Need to click on this guy first and then change whatever you want to see. So this is the velocity very near to the, what do you call it? Very near to the sphere. And here is actually, yeah, we can actually choose the magnitude of the velocity, x, y, or z. Yeah. Okay. Now this is not interesting because we cannot see flow and everything. What we want is actually the solid, but everything is inside. So how to do that? We just right click here and then section. And then let's say our section should be normal to y. And then we click, right click and update. Click positive. We still do not have anything because this solid, the original one, is covering everything. So we untick on this one and then right click update. Okay. All right, this should be the other side. Clip negative because positive is on the left. We want to keep the right one, the right half. Right click and then update. Okay, now from here we can show the things. So this is actually, if you want to see the mesh, so this is the mesh. You can see in the around the boundary we have more layers because we did this one, BL, boundary layer. That's why here we have more of elements around the boundary of the sphere. Okay, so if I want to show the velocity, this is the velocity. Let me hide the mesh. So this is the velocity. Okay, and then what else? Again, we can show the magnitude or the directional velocity. Okay, and we can see here, this is one. The inlet velocity in y direction here is somewhere 0. Okay, let me show the magnitude, and almost you can see the color 5 because we put the inlet to be 5, right? So this color is almost similar to this one. Okay, now next is, this is if you want to have more values, we can control up to 30, I think. Yeah, 30 is the maximum. And then this one legend, we can put it down here if you want. And we can also control the maximum and the minimum. Okay. Now, if you want to have vector, no, this not, we don't have any vector here. We can add actually vector or streamlines from here. So let's say streamline, and then the source is the plane, and then I need to find the points of the plane, or I can make it a circle, and then the center here is minus 100. The normal, it's in x direction because in x, and then the radius 1 is enough because this one is in millimeters. Update. Where is our guy? I cannot see it. Direction forward, x, center, normal to x. Oh, okay, this one, it should be minus 0.1 because I forgot now we are dealing with seconds. So you can see this is the input. This radius is also very big. Enter. Okay, and now we can control the number of these segments. Right. This one actually should increase the number in the radial direction. So we can see here the streamlines. So if I hide this one, you can see the streamlines. Yeah, actually this streamline should be like a plane. But yeah. So this one 0.0, 0.1, 0.3. I'm not quite sure about how to make this plane from 3 points. So anyway, that's why I stick with the circle, because it is much easier. And also for this streamline, you can see the color is yellow. If I want to show the velocity, actually I can control here. So now you can see it's actually showing the color of the velocity. Okay. If I show this one, it will not be very visible because this section also has the color. So I can just right click here, and then, or I can just, yeah, I can click on this guy, and then instead of velocity, I just put the part ID. Click on the right side. Where is everything? Yeah, I think it's better to hide, then you can see much more clear. Okay, and yeah, this is a streamline. If you want to increase, you can just increase here, then right click and then update. Then you can see we have more now. So yeah, I think that's all, I think.
MashaAllah, you worked very hard and made something out of it.
Yeah.
You have worked very hard.